Well, good day, everyone, and welcome to another offering from our Construx webinar series. I am your host, Mark Griffin, the host of Construx Inspect and Adapt podcasts. I'm excited to introduce today's webinar, Improving Software Quality and Productivity Through Design by Contract, presented by Construx's principal consultant, Steve Tockey. So let me tell you a little bit about my friend and colleague. Steve is a longtime member of the staff here at Construx, having worked in the software engineering arena for almost 4 decades. At Construct, Steve applies his deep experience in object-oriented development, model-based requirements and design, software engineering economics, development process, project management, estimation, and software quality to help a wide variety of clients in applying their best practices throughout development and maintenance. Steve has also been an adjunct professor in the Master of Software Engineering program at Seattle U and is the author of 2 books, his most recent book being How to Engineer Software, which shows how software can be developed and maintained under a true engineering discipline. A couple logistics points to make at the beginning here. Feel free to ask questions in the chat or the Q&A, and we'll address them as we can. And Steve also indicates that he will have some time at the end as well. So let's frame today's topic, Design by Contract. It is used by advanced developers to lower defects and reduce complexity, making development faster. First published by Bertrand Meyer in 1986 as part of his work on the Eiffel programming language. Design by Contract is language independent and shows significant benefit across all programming languages. This webinar will discuss how and why Design by Contract is so beneficial, with particular emphasis on how it reduces code defects, makes remaining defects easier to find and fix, and reduces complexity. Well, how are you doing this morning, Steve?
Doing good. How about you, Mark?
Well, I'm doing well. I'm really excited for this topic, and I really am going to lean in and listen in and learn something, and hope everybody else does as well. So, your ball. Take it away.
Okay, thanks, Mark. Welcome, everybody. So to start things off, at various times, such as Inspect and Adapt Episode 5 on design patterns and fundamental principles, there was a Lunch and Learn series on the How to Engineer Software book, and other times, I've referred to Design by Contract as, quote, another topic for another time, end quote. Well, that time has finally come. So obligatory legal stuff, fine. As Mark mentioned, Design by Contract, which is actually a trademark term, by the way, was first published by Bertrand Meyer in 1986 as part of his work on the Eiffel programming language. It's shown significant benefit across virtually all languages since then. I've been using it myself seriously for the last 20 or so years to great advantage, and it's a key element of my personal coding standard. And so, as I said, we'll talk about how and why Design by Contract is so beneficial. Basically, it's allowing you to think about the code in a way that leads to fewer defects in the first place. The defects that do appear tend to be easier to find and to fix, and we're less likely to re-inject new defects when fixing old defects. It also helps significantly reduce the effects of code complexity. So that's where we are going. I want to start talking about state of the software practice, what's going on today. We'll move into contracts in the real world, because contracts in software are somewhat derived from the idea of contracts in the real world. Then we'll move into contracts in software, what they are and why they're so valuable. Now, I'll just warn you that there's definitely a lot more to the whole Design by Contract story. This is all we have time for today. There are many other directions we could take this if we have more time. So let's start by talking about what's happening in the software industry today. Irrespective of agile versus plan-based development, waterfall, etc., requirements, design, code, and test are already recognized as the major drivers of software project effort and therefore cost and schedule. The only real difference is when the work is being done. When you're following a waterfall type life cycle, you're doing the requirements in one big upfront phase, design in one big upfront phase, etc., etc. Whereas you're definitely doing requirements work on your Agile projects. You're definitely doing design work on your Agile projects. You're just doing them on a per story basis. Now, the point here is that IEEE Computer Society defines 4 kinds of software maintenance. They're called perfective maintenance, adaptive maintenance, corrective maintenance, and preventative maintenance. Basically, perfective maintenance is taking the product and making it better. Adaptive has to do with moving to new environments. We're porting off of this platform into that platform. And those are what, like cholesterol, I would call the good kinds of cholesterol. It is good to perfect, it is good to adapt. Now, on the other hand, corrective maintenance is fixing things that were broken that were found by the customer. Preventative maintenance are fixing things in the software that's broken that were found presumably by the development or test organization before the code actually got delivered. And again, like cholesterol, these are the bad kinds of maintenance. Fixing mistakes that the customer found, fixing mistakes before the customer, it's still a matter of fixing mistakes. Now, my point here is that this measure, rework percentage, R%, is a measure of bad maintenance, the bad kind of maintenance. How much of the project effort, if you would think of it in hours, how many labor hours were spent on corrective and preventative maintenance of the code divided by the total effort spent on the project. Now, the unfortunate fact is that of 5 organizations where we have measured very precisely, varying in size between 50 developers and 350 developers, that we're seeing rework percentages that average or weighted average is 61.2%. So what this means is that if rework is 61.2%, that all the requirements, design work, code work, and testing work can't be any more than 39.8% or rounding to 40%. Therefore, the single largest driver of cost and schedule on a typical software project is this bad cholesterol, this bad rework, the corrective and preventative kinds of maintenance. And as one professional acquaintance of mine would say, essentially for every hour of productive work, there's 1.5 hours of rework. And so there is the major driver of software project cost, effort, et cetera, et cetera. And so it's worth pointing out that unmanaged complexity is also a major compounding factor in software projects. And so the point today will be to show how design by contract is going to help us reduce rework and help us manage complexity. And that's where the software quality and productivity improvements in the title are really coming in here. So that's where we're going. Linguistics, the study of language. Now, normally when we're talking about linguistics, we would be studying natural language like English, French, German, Chinese, et cetera, but everything in linguistics is also entirely relevant to programming language as well. Now, we're not going to go across the broad spectrum of linguistics. We're just going to focus in on 2 specific elements, the word syntax and the word semantics. Syntax is about structure, semantics is about meaning. And to emphasize, I've got a couple of examples over here on the right-hand side. So example 1, everybody who speaks English, presumably everybody on this presentation, can read the top sentence here, the sky is blue. That's fine, okay? Here in Chinese, Tian Kong Shi Lan Sida. Tian Kong, the first 2 characters, sky, should, the 3rd character is, Lan, blue, Sida, colored. So sky is blue colored. If anybody happens to recognize Korean, Hanul un paranseki da. Hanul sky, the un here is a marker that marks this noun to be the subject of the sentence. Paran blue, say color ita is. Sky as subject, blue color is. I give you this book. I give you this book. I as subject, to you as indirect object, book as direct object, give. I, to you, book, give. She drives a car. She drives car. That female as subject, car as direct object, drives. So again, the key idea, syntax is about structure, semantics is about meaning. And for our purposes, what you should maybe notice, hopefully notice, is that the syntax of Chinese is actually comfortably close to the syntax of English, subject, verb, object. Okay, whereas the syntax of Korean is completely different. That in Korean, the verb is always the last thing that you say in the sentence, and that induces the needs for these markers, the subject marker, the direct object marker, the indirect object marker, because you can't tell what role the noun plays merely based on its position relative to the verb, because all nouns will always come before the verb. So the syntax of English, the syntax of Chinese, the syntax of Korean. As I said, Chinese and English, for our purposes, are reasonably close, but Korean, completely different. Okay. Semantics, as I said, is about meaning. So the semantics in example 1 is all the same. Look up, it will tend to be blue, except it's cloudy today and raining in Seattle as usual. Example 2 is all about a book going from one person to another, et cetera, et cetera. But to help emphasize, if you look at example 4, colorless green dreams sleep furiously, this example is credited to a guy named Noam Chomsky, who is one of the biggies in linguistics. But the idea here is that according to all of the rules of English syntax, this is a syntactically correct statement. It is structured according to the rules of English syntax, English language. However, even though it's correct from a syntactic perspective, it is entirely semantically meaningless. It literally has no valid meaning. Good structure, bad meaning. Now, why this is all relevant to us is that what you would call a bug, what I would call a defect, is literally a semantic inconsistency. Let me say this another way, that your compiler is a ruthless master of programming language syntax, and it's of essentially no help with semantics. So unless we start to pay more attention to code semantics, we can't really reduce those semantic inconsistencies, those defects, those bugs. And design by contract is one actually very powerful way to start paying more attention to semantics in code. Programming by intent, a topic for another day, and software proof of correctness, another topic for another day, are other ways that we can do this. But basically, until, as I said, we start paying more attention to code semantics over and above the syntax that the programming language forces us to pay attention to already, that we're not really going to make a whole lot of improvements in quality of software and reduction in defects, because the correctness is a semantic property of software. It's not a syntactic property. Okay. So as I said, contracts in software are somewhat derived from the idea of contracts in everyday life. So let's start looking at everyday real world contracts and then build from there. And so if we define what a contract is, it's an agreement between two or more parties that creates an obligation to either perform particular duties or to not perform particular duties. And so each party is promising something in exchange for some kind of benefit. As long as you, then I. But the subtle part of this is that if you don't, then I don't have to. Okay. So some kind of agreement. You do, then I, and if you don't, I don't have to. Okay. The agreement, the contract may be explicit or implicit regarding what the duties are, and may be explicit or implicit regarding what the penalties for noncompliance are. And so to get into some, as I said, real world examples here, examples of explicit contracts, legal, financial. If you're going to buy a house, if you're going to lease a house, if you're going to rent a house or apartment, if you're going to buy, lease, or rent a vehicle, an airline ticket is actually an explicit legal contract. Internet service, cell phone service, licensed software. These are all examples of basically sign on the dotted line. As long as you pay, then you get, but if you don't pay, that you don't. Our whole criminal code is basically penalties for noncompliance. As long as you don't break the law, then everything's fine. But if you do break the line, then you shall be fined not more than some amount or imprisoned not more than some amount of time. So long as you stay out of jail. However, if you, then you can go into jail. Now, on the other hand, there are plenty of implicit, unwritten contracts that are in play in society and culture. Personal hygiene, how you dress, how you present yourself, public behavior, politeness, don't lie, cheat, steal, avoid others when you're ill so you don't spread whatever disease, don't yell fire in a crowded theater, tipping, et cetera, et cetera. Those are all examples of essentially implicit contracts. They're not written down for the most part. They're not something that you sign, that other people sign. It's just sort of by default, we all kind of implicitly agree to behave certain ways. Okay, now, the reason that explicit contracts become so important because there are problems caused by implicit contracts. Obligations can and do vary significantly by context. The social obligations, by location, what is accepted and expected here is not always expected and expected there. Favorite examples here are if you burp after a meal. Tipping behavior varies quite radically across the world. Quite interesting if you're ever in Thailand. It seems kind of weird to us Western people, but don't ever point the bottom of your shoe at somebody because it's very disrespectful of them. And so anytime you're sitting, anytime your shoes or your feet are not pointed at the ground, be careful where the bottom of your feet are pointing because people will take that as an insult. It's perfectly fine here. It's not fine there. What's accepted and expected then is not always accepted and expected now. Comparing things in the boomer generation and things in Gen Z as examples of then versus now. Leading to the issue that one of the parties may violate this contract, this agreement, unintentionally. I didn't mean to insult you by pointing the bottom of my shoe at you. Because it means nothing to me. I didn't intend to. So that's one thing. Well, one of the parties may intentionally push an unstated limit or an unclear limit, with the common example of that being the quote, "It's better to ask for forgiveness than to ask for permission," because the contract isn't really clear. If I violate the contract, I'll just say I'm sorry rather than say, "Hey, is it okay if I," and if you say no, then I won't. Okay. One of the parties can even deny the terms of an agreement, as in the whole bait and switch situation. You thought you were going to buy this, and what you actually got was that, because what they did was change the agreement because it wasn't written down. And you can't point to anything that says, no, this was our agreement. Parties can even deny the existence of agreements in the first place. When did I agree to that? I certainly don't remember that. And so part of the point here is that we'll actually start to see similar problems when we look at implicit contracts in software. Okay, so let's move into explicit contracts in code. Take the idea of explicit contracts in the real world and move into the software world. Again, so long as you, then I, but if you don't, then I don't have to. So again, 1986 or so, Bertrand Meyer, part of the Eiffel language, been exported well beyond that. But the idea here is that a function, a software function, should be understood and in fact specified in terms of its contract. So long as that's the required side of the contract. What does the calling programmer need to be sure to make true before they call this function? The guarantees, the true, what needs to be true afterwards. So long as before you called me, then I will. But if you didn't, then I don't have to. There also turns out to be a part of the contract. Again, we'll go into this in a little bit more detail later, but the idea of invariant conditions, which are essentially always true. But part of the important point here is that the contract should only state things that are not already automatically enforced by the language. If I'm already in a strongly typed language, Java, C Sharp, don't tell me about the data types of the parameters, because the compiler is already going to enforce data type compatibility. And so just to point out as a first example right here in the shaded area, this is a little code sample. Okay, public void open paren double initial amount, close paren open curly brace. That is what we would call the signature of the function. The name of the function, the number of parameters, the data types of the parameters in strongly typed languages, and the return type. That signature of the function, the point here is that that is a declaration of the syntax of the interface. It declares the syntax of the interface. Now, clever use of naming may imply semantics, but it's not very precise. It doesn't fully specify semantics, and that's where the contract comes in. And so you can see literally the contract is inline in code in comments, but requires don't call this function, hey, Mr. or Ms. calling programmer, don't ever call this function if the initial amount is not greater than 0 and less than $100,000. And so long as you do that, then the logic of the function is that if you called me when the status of the account was closed, then when I'm all done, the account will now be an open account, and the balance of the account will be the initial amount that you specified. Otherwise, there will be some error reported and nothing else has changed. So if you, then I, but if you don't, then I don't have to. Okay, so what is required of the calling programmer before you called me? And if that was true, then here's what I guarantee will be true afterwards. Now, keep in mind a couple of quick points here. As I said, if you don't, then all bets are off. If you call this function with an initial amount that's outside of that range, this function is free to do whatever it wanted to, up to and including crashing the system. And I need to be very careful to point out here that the reason the system crashed was not the fault of this function. It's the fault of the programmer who wrote the code that called this function. I told you what you needed to do. You didn't do it. The system crashes, your fault. Now, system crash is a very obvious problem, but the issue of semantic inconsistency, defect, bug is that quite often these the problem is a lot more subtle than system crash, blue screen. Okay, a key element of the contract is that it's non-procedural. Okay, if this is true before, then this will be true afterwards. Okay, there's no procedure, there's no algorithm here. Whatever algorithm a programmer chose to get from requires to guarantees is up to the service side implementing programmer. And again, I'll give you examples later, but again, I want to emphasize that the contract is not an algorithm. It's what needs to be true beforehand, what will be true afterwards, so long as what needed to be true beforehand was in fact true beforehand. And there happens to be this book by McKim and et al., Designed by Contract by Example, which is an entire book on the topic. So if you want more information on design by contract, aside from there being articles that written by Bertrand Meyer and others, is that there is in fact an entire book on the topic. Okay, so elements of explicit software contracts. On the require side of the contract, there are two kinds of elements. One of the elements is constraints on input parameters as shown here. The amount to deposit must be between 1 penny and $100,000 inclusive. Don't call me with an amount to deposit outside of that range. If you do, bad things will happen. The quantity ordered needs to be greater than or equal to 1. Shipping address is acceptable to postal authorities. A pointer is not null, etc., etc. These are all examples of constraints on input parameters. Beyond the signature telling me the type of the parameter, Are all values included in that type all allowed for that parameter? To the extent that a value is included in the type, but it is not allowable in the function, that would be a constraint on an input parameter as shown here. Constraints on state of execution. The account must be an open account. The log file must be open for write because I might write things into the log file. The buffer cannot be full because I might write things into the buffer, et cetera, et cetera. Again, notice that these are not algorithms. They're conditions, they're assertions, they're propositions, they're predicates, they're logical statements, if you will. Okay, now on the guarantees side, we can have constraints on output parameters, essentially including what the meaning of the parameter is. I will return true only when successful, otherwise whatever. I will return a positive number if it's I will return a negative number if it's not success. I will return you -4 when. And so how can you interpret that return value or values? Again, constraints on state of execution. The log file is no longer open for write because I closed it. Errors or exceptions. I will throw this exception under these conditions. I'll throw that exception under that condition. Possibly, but not often, you can include performance limits in a contract. For example, I promise to use no more than 200 bytes of memory per instance of this thing. I'll return to you in 25 milliseconds or less, whatever. Okay. So as long as you on the require side, then I promise on the guarantee side. And as I said, invariants are things beyond the scope of a single function, things that are more true sort of across the board. They may be system-wide invariants, or they may be, as Bertrand Meyer published, the idea in object-oriented development, the idea of a class invariant. It is something that is always true within the class or always true within the scope of the system. All bank customers must own at least one bank account. All bank accounts are owned by at least one customer. Each bank account balance is greater than $0. Each transaction date is no earlier than the 1st of January 1990. Each transaction date is no later than today. These would all transcend the time of a single function. They would be, again, sort of business rules, if you will, either over a class or over the entire system overall time. Now, the little subtext here may be temporarily violated during while I am executing a single function because things are happening sequentially. There may be things that get out of sync. I may have an account without a customer. I may have a customer without an account. But by the time the function finishes, all of the invariants must be true. We can assume all invariants are true before the function starts. We must also be able to assume that all variants are true after the function completes. Okay. And so what I want to do now is look at some concrete examples of code, function, contract. And so in a class triangle, where we have a static method classify triangle that takes as input a string, which should represent the lengths of sides of triangles, where if all the three sides are equal, then this function should say, hey, that's an equilateral triangle. If only two of the sides are equal, then it should say this is an isosceles triangle. And if none of the sides are equal, then it would be a scalene triangle. If you've been through a couple of my classes like the testing class, this is an example that we use in the testing class. But looking at it from design by contract perspective, notice that require sides is not null. Do not give me a null pointer to the string. The side lengths are separated by at least one non-numeric character. Doesn't care which non-numeric character, it just has to be a non-numeric character separating each of the sides. And so long as you have done that before you called this function, when sides has exactly 3 integer lengths and each length is greater than 0 and the longest length is greater than the sum of the two shorter lengths, and when all 3 lengths are equal, then it returns equilateral. When exactly 2 are equal, then. So the important point here is that what I have here are two constraints on the input parameters in the require side. I have four constraints on the output parameters, which are essentially what you're going to get under these conditions. There are no state-oriented issues in the contract for this function. But I want to point out that there are semantic questions, there are behavioral questions that are being answered by the contract. Can the input string be null? And the answer is no, because the contract says. Can the input string be empty? Yes, because empty string is not null string. And it didn't say you couldn't give me an empty string. If you couldn't give me the empty string, then part of the contract must say not only is sides not null, it can't be empty. What are the valid side length separators? Well, any non-numeric character should be acceptable. Are multiple separators allowed? Well, yes. Can the string contain garbage? Yes. And what happens if so? Then you're going to get back the string invalid triangle. Does the function deal with right triangles? Well, no, it will not tell you if the triangle is a right triangle or not. And basically, under what conditions do I get what responses? And so the point really becomes, if you needed to write code that used this function for whatever reason, what else would you need to know? What else would you want to know beyond what I'm telling you in the contract? And the idea here, the client-side programmer must be able to write their code using only the signature, which is, as I said, the syntax of the interface. What's the name of the function? What are the parameters? What are the types? What are the returns? That's the signature. That's the structure. And the contract, the semantics. So if I give you the signature and the contract, you should understand everything you need to know about writing code to use this function. You don't need to do anything else. Most notably, look at the lines of code between the curly braces on how the function is implemented. It could be implemented this way. It could be implemented that way. It's not relevant to you. It's not important. It's not necessary. If we move over to another example here, so imagine I have a class that deals with strings with an instance variable, the string, and there's a function, there's a member function, a method, convert to float, that attempts to convert the value that's in the string to a value of type float, okay? It doesn't require anything. It guarantees when. And again, I'm back to, there are no constraints on input parameters. There are no constraints on state. There are four constraints on output parameters. Essentially, under these conditions, you get this. Under those conditions, you get that. Can the string be null? Yes, because the contract doesn't say it has to not be null. Can the string be empty? Yes. Can the string contain garbage? Yeah. What is the biggest value? Well, float.max value. What's the smallest value? Float.min value. And again, if you needed to write code that was using this function, would you want to know anything else? Can you, as a client-side programmer, write your code using exactly this? Okay. Another example. What's being required here? What's being guaranteed here? There's one constraint on an input parameter. There's one constraint on an ending state. There are two constraints on output parameters. Semantic questions. Can I be outside of the set of 220 or valid language code? No. What effect does the B parameter have on things? Still another example. I'm not going to go into each of these examples in as much detail, but the idea is hopefully you're starting to see that for every function, I have the signature that defines the syntax of the interface, and I have the contract which defines the semantic of the interface, and that the semantic is non-procedurable. What needs to be true beforehand, what needs to be true afterwards, and so long as that was true beforehand, then the responsibility of this code is to make that true afterwards. And client-side programmer must be able to write their code using only the signature, the syntax, and the contract, the semantics. Other examples, and I just want to point out here that this is one of my hobbies is retro computing, dealing with this particular computer right here over my shoulder. that computer was the very first computer I ever programmed. And if I'm doing the math right, Mark, it's 47 years or so ago. So I've actually been in the software industry 45 years, not about 40, over 40. It's been 45 years since I first started getting paid to write code, or is it 46? Yeah. 1977 June was when I first started getting paid to write code. This is assembly language code. And so forget temporarily, forget Java, forget C Sharp, forget C++, forget Python. Here is assembly code, and I've got contracts in assembly code. We won't talk about what this particular code does. Just it had to do with binary format paper tapes for a basic interpreter for that particular machine, that I needed to make sure that the binary tape and a recreation of it were the same. And so I wrote a program that would compare one to the other, and I had to do it in an assembly language. And yes, I used contracts. Okay. So I want to move over from just contracts specifically, and I want to go beyond that and start talking a little bit about defensive programming. Now, you've probably already heard of defensive programming, but the point that I want to make here is that it's really easy to talk about defensive programming in terms of design by contract, because defensive programming is essentially, quote, require nothing, don't require anything. That the code, the function is able to handle virtually anything that you throw at it without doing bad things. It basically means it requires nothing. Now, the advantage of, well, let me skip ahead here just one moment, one slide, okay? For the same signature, I've got 4 examples here. All 4 examples have exactly the same signature. They have the exact same syntax to the interface. So version 1 requires 3 things, A, B, C, whatever A, B, and C are. It does require those things to be true before you call this function. If they are true, then it will guarantee X and Y, whatever X and Y happen to be. This is just an abstract example. That is the least defensive because it requires the most. Now notice that the function could be written in a way that has exactly the same signature, but now it requires A and B, whatever A is, and it guarantees that so long as C was true when you called me, then I'll give you X and Y. Otherwise, some appropriate response, maybe return an error code. No, can't return error code because it's a void function. But maybe it throws an exception, maybe drop something in a log file, whatever. Okay, it is more defensive because it doesn't require C is true when you call me. Version 3 here, it requires only A. When B and C are true, then you get X and Y. But if B or C is not true, then you get some appropriate response. Version 4 is the most defensive because it doesn't require anything. So when A and B and C are true, then you will get X and Y. But if either A or B or C is not true, then again, you get some appropriate response. Again, the whole point here is for the same syntax of the interface, the semantics are actually different, with there being sort of gradients of defensiveness. Less defensiveness, 1, 2, more defensiveness, 3, 4. Version 4 here is the most defensive. Now, as a consequence of this, the advantage of being more defensive is that I get less fragile, less vulnerable, safer, more secure code, and that's definitely a good thing. However, if we look at the most defensive version here, version 4 doesn't require anything, guaranteeing that when A and B and C are true, then I think it's fairly obvious that the first line of code beyond the opening curly brace has got to be some sort of if check. Is A true? Because if it is true, we got to do this. And if it's not true, we got to do something else. So that introduces a decision, an error checking decision, which is then going to increase the structural complexity of the code. If we are familiar with the idea of cyclomatic complexity, if you're familiar with the idea of depth of decision nesting, that we've necessarily increased the structural complexity of the code by having it do those checks. Increased unit testing. I have to have unit test cases that exercise when A is true, when A is not true, when B is true, when B is not, to make sure that that logic is working correctly. The code is going to run slower because every time you call the function, it has to do that, and increase cost and schedule because there's more code to write, there's more code to maintain, there's more code to test. Well, the point here being is that I cannot always afford to be that defensive. And so when I can afford to be defensive, then by all means be defensive. But if I can't always afford it, then I have to make clear to the calling programmer how defensive I am and how defensive I am not. And there are two ways to communicate that. One is have them read my implementation, and the other way is to publish a contract. And we should definitely prefer just publish a contract. Okay. I do want to quick point out the footnote here. See also there's a Construx white paper titled Evaluating Use of Defensive Programming that goes into design by contract, goes into defensive programming, goes into this relationship, that if anybody wants that, just send us an email, stevet@construx.com. I'll send it back to you, not a problem, if you want that. Okay, we've covered that. Now, Liskov substitutability, the solid principles, SOLID, the L in solid is Liskov substitutability. Created by Barbara Liskov and Jeanette Wing, 1994. I claim that it's impossible to understand what Liskov substitutability is all about and appreciate what it's all about without looking at it from design by contract terms. Now, it is most often formally defined and described in terms of inheritance relationships, but I'll give you a brief taste that it is applicable well beyond just inheritance relationships. Now, what you're seeing on this slide is the formal definition. If T is a superclass of X, then objects of class T in the program may be really, I'm not going to read the whole thing, but that is the formal definition of Liskov substitutability with respect to inheritance. What I want to do is look at it, sort of reverse engineer out the formal definition from an informal example. And so let's say that I've got a mythical client-side programmer, I'll just call him Fred, P-H-R-E-D, Fred, that wants to write code to the published interface of shape, syntax, and semantics. Shape draw, to be specific, because shape draw, I'm giving you the contract for shape draw. What does it require? It requires an open graphics canvas into which to do the drawing. Guarantees that the visible portion of the shape will appear, accounting for panning and scaling and clipping and all of that wonderful stuff. And so Fred, my mythical programmer, is going to write Fred's code to the syntax of shape and to the semantics of shape draw, and therefore Fred's code should work appropriately given shapes. Okay, but in order for Fred's code to still work if it encounters a circle, then circle draw. Is it safe for circle draw to require the same as shape draw? Circle draw requires an open graphics canvas. Shape draw requires an open graphics canvas. Notice that's requiring the same. And so, yeah, that's safe, not a problem there. Could circle draw have been implemented in a way that it doesn't require an open graphics palette? The first line of code in circle draw happens to be, if there is no open graphics palette, then open one, or graphics canvas, then open one and do the drawing there. The important thing here is that is safe. It is safe for the subclass method to require less. Now, keep in mind that from Fred's perspective, that is not accessible functionality because Fred has to deal with shapes, and shapes do require. But to the extent that Mary, this other mythical programmer over here, only needs circles, then Mary can take advantage of the lazy open of the canvas on circle draw because Mary only needs circles. Mary doesn't need more general shapes. It is safe to require the same. It is safe to require less. It is not safe to require more because Fred, my intrepid programmer over here, may not be satisfying that extra thing that circles require that Fred was not aware of looking at shape draw. And so very simply, preconditions requires clause for methods in the subclass may be as strict, require the same, less strict, require less. They cannot be more strict. From Bertrand Meyer himself, a subclass must require no more. Okay. And so if we go back here, let's look at the guarantees. Again, Fred, shape, draw, guarantees visible portion. Now notice circle draw. Visible portion of circle appears. Now notice in shape, it's just the shape. Circle, you get a circle. With the important point here being, this is a stronger guarantee. The subclass is guaranteeing more. You will see a circle, not just any arbitrary shape, any random shape. You will see a circle. That is a stronger guarantee. So hopefully it should be obvious that the subclass could guarantee more. It could guarantee the same, but it shouldn't guarantee any less, because the thing that it is not guaranteeing may be exactly the thing that Fred's code was needing. Okay. Now the other thing here is that the subclass can't introduce any new exceptions. That circle draw can't throw an exception that Fred would not have been aware of, other than what was already stated in shape draw. So again, really quickly, I can't require any more. I can't guarantee any less. Again, Bertrand Meyer, a subclass must require more, no more, and promise no less than a superclass. And oh, by the way, don't throw any new exceptions. Okay. So that in a nutshell is Liskov substitutability. And while this is obviously and intentionally an extreme example, counterexample to illustrate the problem that you can get into. So what you're saying here, Clint Eastwood in one of the quote spaghetti westerns, A Fistful of Dollars, 1964, A Few Dollars More, 1965, The Good, the Bad, and the Ugly, 1966. That Clint Eastwood here is an instance of a class that I'm going to call a Wild West gunfighter. And the question is, can a Wild West gunfighter move? And the answer is, well, yes, they can move. Can a Wild West gunfighter hide? Well, yes, they can hide. Can they show? Yes, they can show. Can a Wild West gunfighter draw? And the answer is, why, yes. Okay, and so if I look back here, shapes, draw, move, hide, show. Well, that's exactly syntactically the interface of Wild West Gunfighters 2. And given that your compiler is a ruthless master of language syntax, it only cares about syntactic compatibility. In other words, can somebody write a subclass, public class, Wild West Gunfighter, extend shape? That's how I would do it in Java. And then provide implementations for draw, move, hide, show. Why, yes, syntactically, their interfaces are indistinguishable. They're identical syntactically. But what is the semantic of shape draw? What is the semantic of Wild West Gunfighter draw? Wild West Gunfighter draw requires the gun in the holster on the hip. What does it guarantee? Well, the gun is in the hand pointed at the target. And these are wildly different, requires guarantees. And so if Fred's intrepid code over here is expecting shapes and rectangles and circles, but actually gets Clint Eastwood, and Fred's code says, my shape, even though it's Clint Eastwood, dot draw, what's going to happen? And the answer is very bad things can happen. And so the term is accidental polymorphism. It simply means that things are syntactically identical, but semantically quite different, and bad things are about to happen. Okay, so that being a counterexample. Now, really quickly, I just want to say that if I go back to my spectrum of defensiveness, notice that the most defensive version, let me start the other way. If I start with the least defensive version of the implementation and I rewrite the method code to make it more defensive, then it requires less and it guarantees more. And if I move it one more step, more defensive, it requires even less, it guarantees even more. And so if I have a more defensive implementation of a function, it is Liskov substitutable with the less defensive version. If I have a more defensive version, and for performance reasons, complexity reasons, whatever, I have to make it less defensive in moving the other way, it is not Liskov substitutable. In other words, I could introduce some very subtle defects into my code base without knowing that I've changed the contract in a way that can easily introduce these very subtle, hard to find defects. Okay, so there may not be any inheritance within kilometers of here, and yet Liskov substitutability is still relevant. That's my point. It goes well beyond just inheritance relationships. And so what I want to talk about now very briefly, development and maintenance under design by contract. If you are the service side developer, then you publish the function signature in the contract and you implement the function consistent with the published signature in the contract. And then you maintain the implementation consistent with that published signature and contract. All code changes that do not affect the published signature and contract are explicitly safe. You are guaranteed that whatever change you made to the code would not break any client-side code that used the same syntax and semantics. However, if a change affects the contract, if it affects the contract in a way that is Liskov compliant, in other words, it doesn't require any more, it doesn't guarantee any less. You rewrote the method implementation in a way that it didn't require any more, it didn't guarantee any less, then it's explicitly safe of you to do that. However, if you rewrote the code in a way that is not Liskov substitutable, then there has to be a notification, there has to be a negotiation with the client-side developer. Hey, folks, I've changed the contract. You better deal with the fact that I am now requiring this. I am now no longer guaranteeing that, whatever it is. And so what you're seeing on the left side here is how the client side, how the publisher of that functionality should behave. Now on the client side, on the consumer side, I would write and maintain my client code consistent with the server-side signature and contract. I program to the interface. I do not program through the interface. I can focus only on the client-side complexity. I only have to deal with the complexity between my curly braces. It is explicitly safe for me to ignore any and all service-side implementation complexity. I don't care how complex their code is for them to satisfy their contract. I just write my code to the contract and it ends there. And then I can be confident of ongoing service-side code maintenance won't break my code so long as they didn't change the contract in a non-LSP compliant way. But if there was a need to change their implementation in a way that was not LSP compliant, then again, I have to be open to addressing and negotiating that change. Hey, something that was not required before is now required. Something that was guaranteed before is now not guaranteed anymore. I have to be open to the fact that that could happen, that I could get that notification. But this is exactly where the quality and productivity improvements that I talked about in the title are coming in. You call it a bug, I call it a defect. It's a semantic inconsistency. Design by contract is explicitly focusing on the semantics of the interface. And so the client side writes code to the interface, the server side writes code to that semantic. We are less likely to write defects into the code because we're looking at exactly what the code needs to do in terms of the contract and both initial development, long-term maintenance. If there is a defect, it is easier to isolate. Which side of the contract is the failure on? Did you not satisfy the contract? Did you not satisfy the requires? Did I not satisfy the guarantees? And the productivity comes in partly because there's a significant reduction in complexity alone, because I, as the client-side developer, I now no longer have to worry about the complexity between their curly braces. I just write to the contract. I don't worry that it's a memory resident linked list under the cover. I don't worry that it's a bitmap. I don't worry that just I write code to this published behavior and fine. And the rework percentage gets reduced because there are fewer defects, which also increases the velocity. So I have a complexity reduction, I have a defect reduction, my productivity goes up, my quality goes up because we're paying more attention to the defects, we're avoiding the defects, we're making it easier to find and fix the defects, and all because we're now using contracts. Okay, so problems caused by implicit contracts in code. Well, there's the time, the effort, the complexity burden on the client-side developer. If I didn't tell you what the contract was, then you have to read my code. A function without a contract is the moral and ethical equivalent of forcing you to take apart your car to understand how the car works before you can drive it. If the interface to cars was not as standard as it was, and you bought a new car that had a non-standard interface and didn't include any user documentation, what happens when I press this button? You have to take the car apart. This is literally what we have to do with code every day. I want to use that function. I don't have a contract. Well, what does this parameter mean? Can I call this with a null parameter? Can I call it with a negative value? What happens if? And so it really boils down, from my perspective, without design by contract, there can be no encapsulation. So as much as we talk about encapsulation being this lofty principle that, you can talk to encapsulation until you're blue in the face, but if I say, show me contracts in your code, then literally I'm going to slap you because you're saying encapsulation, but you're not doing it because there are no contracts. Without design by contract, there is no encapsulation. Subtle, hard to find defects. Again, because there was no explicit contract that said that the value of this parameter had to be between here and here, and you didn't give me a value between here and here, and it wasn't obvious that the value needed to be here and here. Now, certainly, if the code blows up, blue screen, no pointer except, these are very obvious problems, but quite often the problems introduced by contract violations are really, really subtle. Okay, long-term server-side code maintenance inadvertently changes the contract. You change the code inside the called function in a way that has it require more, that has it guarantee less. But we don't communicate the fact that the semantic did change and allows its substitutable change because nobody recognized that it happened. Finger pointing in distributed development. Oh, wait, sorry. Time and effort. Oh, by the way. Okay, I should have gone there before. Sorry. But maintenance cost saving. Large programs that are using encapsulation effectively are easier to modify by a factor of 4 than programs that don't. So the point here is really that in a typical organization, only 20% of the development budget is being spent on building new code that didn't exist before, building new systems, new programs that didn't exist before. 80% of what we're spending is on maintaining systems that have already existed. We're version 2, version 3, version 4.2, version 7.9, whatever. And so if somebody comes along and says, hey, I can reduce the cost of development by a factor of 4 without affecting maintenance, then okay, that reduces the total cost of ownership by 15%. And I'm not going to sneeze at that. I'm certainly okay with that. But on the other hand, suppose somebody came to me and said, hey, here's something that won't affect your new development, but what it does do is cut your maintenance by a factor of 4. That now I'm basically cutting 60% of the total development effort, the total cost of ownership of the code. We have 4 times the leverage in maintenance that we do in development. That's the point. And so even if design by contract didn't affect new development speed, the fact that it increases my maintenance velocity by a factor of 4 means that this is hugely important stuff. This is one of the few principles indisputably proven its worth in practice, especially in evolutionary environments. And so just go back here quickly, finger pointing in distributed development. And so the point here is globally distributed development, worst case. We over here, our team, they over there, their team, we've agreed on the syntax of the API. Here are the names of all the functions. Here are the parameters. Here are the data types on the parameters, et cetera, et cetera. Fine. We write our code to the published syntax, the agreed to syntax, and our interpretation of the semantics. They write their code to the same syntax, but their interpretation of the semantics. We compile the code, we link the code, we build the code, fine, because the compiler, the linker, the builder, they only care about syntax. Everything compiles, builds, links just fine. But when we start running, then boom, crash. Isn't this the typical initial startup? And what happens is that, hey, your code is broken. No, our code is perfect. It's your code is broken. No, you would misunderstand. Our code is perfect. It's your code that's broken. Well, wait a minute. Shouldn't you be able to accept a null pointer? Well, why in the world would you call this code with a null pointer? We're arguing semantics. And so the point here really boils down to is that if the API that we agreed to not only included the signatures, the names of the functions, the parameters, the data types, but also included the contracts, then you write your code to the agreed to syntax and semantics. I write my code to the agreed to syntax and semantics. Of course, it compiles, of course, it links because everybody is following the same syntax, but we should have a much higher probability of it actually executing correctly because we agreed on the semantic through the contracts. And if there was a problem, we can start talking about, oh, whose code violated the contract? Oh, why, yes, I did call you with a null pointer and the contract did say no null pointers. Oh, the contract did say I would give you this. Oh, I see our code doesn't give you this. Our fault, apologies. And so a lot of the problems that we see in distributed development will then go away or at least be significantly reduced because we have contracts. Other benefits that we don't have time to go into, this is again, another story for another time. Helps expose cohesion violations, single responsibility at a method level. I can now start considering doing functional unit testing. That the vast majority, exclusively unit testing, is structural testing, statement coverage, decision coverage, et cetera, that if I have the contract, then I can start thinking about testing to the contract. And because the contract doesn't say anything about implementation, it is by definition functional or black box testing. So all the advantages that I get out of a functional perspective on testing is now available at a unit test level. Assertions in code can be based on contracts. There's an approach that I call programming by intent. If you're familiar with Code Complete by Steve McConnell, he calls it pseudocode programming process. It works hand in hand with contracts. If you've ever heard of, or if you're interested in the topic of software proof of correctness, I can prove that my code is not even capable of giving you an incorrect answer. It must give you the right answer. So long as you, then I, that very much depends on the contract as the foundation for building the proof of correctness. We can talk about how it goes into the idea of use case specifications, but again, we don't have time to. So we can go well beyond the advantages that we talked about here in terms of advantages that I can get out of design by contract. So let me quick go into summary mode, then I'll open the floor for questions. So we started with the idea of state of the practice today, about 61% rework, meaning that no more than about 39% productive work. 39 out of every 100 labor hours on the project are productive. 61 are unproductive because of the defects, many of which are consequences or direct result of not doing design by contract. And again, complexity rears its ugly head. So we talked about contracts in the real world, explicit contracts, implicit contracts, problems caused by implicit real world contracts. We moved into contracts in code, how I can now make the contract an explicit part of the code, how that gave me a basis for easily understanding defensive programming and LISCOB substitutability. And we talked about how if I'm developing and maintaining under a design by contract discipline, how that reduces the probability that defects show up. It makes the defects easier to find and fix, reduces the probability that I have re-injected defects, and it vastly reduces complexity, which is again where the productivity and quality increases are coming in. We got quality problems, we got productivity problems caused by implicit contracts, and I just mentioned there are other benefits for another time. And so hopefully you now have a much better understanding of what design by contract is and how and why it significantly improves quality and productivity in software development and maintenance. And on the slides, there were some references that if you wanted to track down references, fine. And so let me open it up to questions now.
We still have some time for questions. There are a few that came in through the chat while you were in process, and some of them I'll try and paraphrase a couple from Devin and Jesse. They talk about the placement of this information in terms of contract language versus comments, and things like, can unit testing describe the same thing as contract comments? How does this contrast to Java doc, PyDoc, JS doc, etc.? It's a question really about where do comments go, or do comments become out of date, things of that nature. So I think in general, just how do you see them in terms of placement and structure?
Okay, so there's actually a lot of questions involved there. And so let me really quickly just pull up an example here. Okay. And so notice how the contract is in line with the code itself. Maybe it's just style, but I think it's better to be putting the contract, the semantic after the syntax. Let me declare the syntax, then let me follow that up with a definition, the declaration of the semantic. It seems much more natural that way. Java doc, Doxygen, etc. Apparently they want you to be putting some of this before. I don't know. I would consider that to be a style issue more than anything, and so I'm not gonna be really nitpicky about that. But it is an important point that the contract and the signature are very close to each other. And to the extent that I can take advantage of tools like Java doc, Doxygen, etc., to give me an extract of the signature and the contract, then I would definitely want to take advantage of that. However, I do want to pile on here with the issue that when I see most people using Java doc, Doxygen, etc., the issue is that they're essentially just repeating what the signature says. Okay, so public static string classified triangle string sides. Well, the next line is going to talk about how the sides parameter is a string. It doesn't talk about any constraints on string. The sides can't be null. The lengths have to be separate. It gives nothing beyond what, and so for that standpoint, Java doc, Doxygen, etc., they tend to be fairly useless.
Okay.
Now, there were a whole bunch of other things. Could I do this with testing? Not in the same way. Whoever asked that question, again, stevet@construx.com, send me an email, and what I can send you back is a white paper on the topic of how design by contract relates to BDD, behavior-driven development, which is a special case of ATDD, acceptance test-driven development. And so I just work an example side by side. Here is the function, here's the contract, here's how we would test it in a BDD way, here's how the test cases, and notice how these are in sync. But the point that I want to make is, once you read that paper, you see how it is much more convenient to be describing the behavior through the contract than through a set of test cases. It's much more obvious.
Okay.
There was the issue about things getting out of sync, the things getting outdated. And so again, really quickly here, that given what developers tend to be paid, Developers tend to be paid well higher than the standard income, sort of the median income. And so basically what I'm arguing here is you are paid professional wages. I expect professional behavior in exchange for the professional wages. And part of the professional behavior is keeping contracts in sync with code. To let things get out of sync is unprofessional. When you look at how important the contract is in terms of quality, in terms of productivity, it is unprofessional to let the contract get out of sync. And if I see you behaving that unprofessionally on my project, I'm going to fire you.
Okay. Let's see. Greg asked, are there ways to force the compiler or other CI steps to help with defensiveness or contracts?
Well, okay, so two different questions there. Now, again, notice that the contract is all in comments. That we don't, I mean, it would be really nice if the contract were more formal, if the contract were part of the programming language. In other words, have the compiler actually interpret the contract. And we're just not there yet. I don't know necessarily that we would ever be there. So that was one half of it. But the other one, in terms of having the compiler enforce more defensiveness, and the argument there is no, you don't want it to. Okay, part of the design of a function is a decision about how defensive the function can be. The defensiveness, how defensive can we afford to be? Because as I said, okay, in going more defensive, it increases the complexity of the code. I can't always afford to be more complex. I can't always afford more unit testing. I can't always afford the code running. So I cannot always afford for the code to be fully defensive. The more defensive it is, the slower the code is going to run. I can talk about companies that have written systems where the coding standard was all functions must be fully defensive. And they're slower than molasses on a cloudy day because of the defensiveness. And so you don't want it to be 100% defensive. You do need to communicate how defensive it is, but how defensive it should be is really a design decision.
Okay. I want to be respectful of people's time here. I'm going to trim it down to one last question before we wrap here, Steve. How do you know that you've reached a common understanding for the semantics? It's easy for people to agree on a statement in a document, but have complete different understanding for what that statement means.
Well, that's an interesting question because when we talk about software proof of correctness, okay, in order to support the proof of correctness, the contract actually has to be really precise. It can't be sort of, I guarantee that you have a well-formed instance of this class. That's not nearly precise enough. And so the issue here is that because there's still, even though this started in the 1980s, in 1986, there's still, if you will, a lack of maturity, for lack of a better word, in terms of how sophisticated contracts are, because we haven't been using them enough to really be able to say this is the right level of formality in a contract. More formal is better for some purposes, it's worse for other purposes. But if we had an agreed on level of formality that said, oh, okay, requires this, guarantees that, and it cannot be interpreted because it is a formal specification, then we're all fine. I hope that answers the question.
Okay.
To the extent that there were other questions that did not get answered, again, I gave you my email address a couple of times. Just shoot me an email. We can have a discussion about other questions that didn't get answered here.
Okay, I appreciate that, Steve. And we can capture some of the Q&A and chat things, and you can, if you want to respond to some of these folks, we can. I think that's
okay.
going to be it for today. I do appreciate your time and effort here, Steve. I think, we have joked internally that this took a long time before we finally got this out, and I'm glad we finally did, because I think it's a very important topic, and I think people really enjoyed it. based upon the number of